I just record the lecture.
Oh, okay.
Today's lecture is a continuation of the methods 2A, and we are going to continue to discuss briefly the KD, which we recall reflects affinity, and then go in to talk about inhibition, understanding a K sub I, more so from the perspective of an enzyme assay. And I apologize that the slides are not specific for neurotransmitter evaluations of Ki, but the point to be made, the practical application, will come forth from this as we glean through the information on the slides. So let's continue with our discussion of understanding, whoops, pushing the wrong buttons here, understanding the radioligand binding assays from the perspective of affinity, KD, the concentration of ligand at which you get 50% of the binding, and the last couple of slides that we had looked at in the previous lecture took us to the point of understanding that the KD, 1 over Ka, is useful in determining concentrations to use in biological assays. And this is the point that I had made there, that using the KD for a drug as a starting point for a concentration assures you that you will not activate any more than 50% of the capacity of the receptors within your biological system. There's no guarantee on that, of course, but it is a good starting point and it is reliable. So the KD is that useful measure to describe the strength of the binding or the affinity between the receptors and the ligands, and that's why it is, in that essence, reliable, although we know intact biological systems are going to give you more challenges, say, than homogenized purified receptors. But we take that into account when we're thinking about why a certain concentration of a drug or dose of a drug was used in a particular study. We would turn to the KD, and now as we proceed, we'll see to the Ki. There was this example of evaluating the affinity of an antibody and an antigen to see what that might be, or to a TCR, T-cell receptor, plus the major histocompatibility peptide, and the KD for the antigen antibody was 10 to the minus 7 to 10 to the minus 11, and for the T-cell receptor MHC peptide, it was 10 to the minus 6. So which has the higher affinity? The higher the KD, the lower the affinity. So 10 to the minus 6 is a higher concentration. It is 1 micromolar rather than the 0.1 micromolar for the antigen antibody. So the antigen antibody does have a higher affinity binding than does the T-cell receptor to the major histocompatibility. So these calculations, these kinetic estimations on the behavior of the systems carries over, as we said, from enzyme assays to receptor assays to any interaction between biological molecules, essentially. So we had discussed the K1 and the K2, and they're going in the opposite directions, as you recall. The K1 toward the formation of the antigen and the substrate and enzyme, to the enzyme plus the product, or the drug and the receptor, free, unbound, toward the bound form, and the K2 was in the opposite direction. So following through this in the simple formula of B equals A plus B, then it'll tell us the strength of the binding, That is, the complex AB more stable than its individual parts? So at equilibrium, the K2 times the concentration of the bound equals K1 times the unbound, the product of the unbound concentrations. So remember that these square brackets mean concentration, so they would be in units of concentration. So the dissociation constant from that approach would be K2 over K1, and this again, immediately you should see the reciprocal association between the two directions when we solve for that algebraically, and that gives the KD. So the 1 over KD is the affinity. So this constant indicates the strength of the binding in the terms of how easy it is to separate the complex AB, that is the dissociation or the off rate. So the larger the K2, the higher the KD, the more it likes to be dissociated rather than associated. So if a high concentration of A and B is required to form AB, that indicates the strength of the binding is low. The KD therefore would be high micromolar. Remember, concentration as more of A and B are required to form the complex bound forms, the AB. So it follows that the smaller the KD, the stronger the binding. So 10 to the minus 6, or 1 micromolar, indicates weak binding of the T cell receptor and the MHC peptide, compared to the 10 to the minus 9, or 1 nanomolar, for the antigen-antibody complex. So this was a little test to see how well we understood this relationship between KD and affinity. The higher the KD, the lower the affinity. And that brings us to this table, just to look at how some of this information might be reported. The source of these tables are shown above. The first table, Table 1, is showing the saturation parameters of tritiated Wei 100635 binding to the rat brain sections. This Wei 100635 is a serotonin 1A type antagonist. And we note different brain regions and the KD, again in concentrations of nanomolar. So right away we see nanomolar in that these are 1 point some number. So none of them are 2 or greater nanomolar. So we see that those are really quite low KDs. So we would feel that we're probably dealing with something that has pretty high affinity. We see that the the KD is not so different in all of these regions, and indeed they had a small n of 3, but they did not have a statistically significant difference in any of these different brain regions. The upper 3 are of the hippocampus, and the lower one is the location of the serotonin cell bodies, as you recall, in the brainstem. And then the B max is in units of femtomole per milligram of tissue. So femtomoles of receptors, or in essence, molecules within the tissue with the capability to bind the ligand, in other words, receptors. So these numbers don't mean much to us. I mean, what are 209 femtomoles of serotonin receptors per milligram of tissue? So the actual number might not mean so much unless we worked in this field for a long period of time and we're very familiar with it. But what it does allow us to do is to compare between the different regions, and none of these seem to have a significantly different number of serotonin 1A receptors when compared to the other areas. Next, we look at the Table 2, the affinities. So you see that Table 1 is the saturation parameters, so you can almost picture the graph of the bound versus the concentration, giving that graph where we saw the KD and the B max being displayed, and the B max referring to the maximum binding indicating the number of receptors. Now let's think about affinities, and we see that the Ki is presented in this sense for nanomolar concentrations of the 1A beta adrenoreceptor ligands for the 5-HT1A receptors in the rat and the human brain. So let's see if we can make some sense of this table. So it was found once the serotonin 1A receptor was identified and characterized, isolated, that some of the beta adrenergic receptor ligands actually did bind to it and have a biological effect. So pindolol, pentbutylol, and tertadolol, ooh, that was a tough one, are three examples of beta adrenergic ligands that do bind to the 5-HT1A receptor. They are competitive in their nature to bind when they are used to knock off the tritiated Wei 100635. So it's an inhibition assay where you work under these same parameters above for the same brain regions so that you know you get saturation and equilibration, and then you look for a concentration of these drugs that will inhibit the binding of the tritiated Wei. So this would be a curve with a negative slope, as we predict. As we increase the concentration of plus minus, in this case the mixed form, and we see the negative and the negative, so this would be RL, and then the LL forms of these drugs. The pindolol inhibits 50% of the binding of the Wei compound at 8.5 nanomolar concentration. So this is the Ki for this drug. If we were comparing the Wei 100635 to be able to inhibit the binding of serotonin, radiolabeled serotonin, then we would find the Ki for this molecule. But this is the Ki for these molecules relative to the this Wei compound. So it's very important to understand what the Ki is being calculated or measured against. And we see that the Ki of the pindolol is not very different as we go across the regions. It looks for the CA1, it might actually be, it looks like they've got notation of statistical significant differences. 14.4 in the human looks like it's higher than in the rat, but for example, the dorsal raphe is not a significant difference between rat and human. So this exercise is characterizing the efficacy of this serotonin 1A antagonist, thought possibly to be very useful in treating anxiety and panic, or possibly even helping to modulate endocrine disorders in rats and in humans, to make a comparison to see how useful the rat models are for studying similar characteristics relevant to human conditions, like I said, anxiety and panic, and possibly in neuroendocrine disorders. Most likely the first two. So the other drugs, the penbutylol and the tertadolol, we see if we just look at the rat CA1, you need a higher concentration to inhibit 50% of the Wei compound. So this would have lower affinity for the 1A receptor than does the pindolol. So we can make that same type of a comparison. The higher the PI Ki, the concentration at which you get 50% inhibition, so higher concentrations required than the affinity or the potency to inhibit the binding of the Wei compound is less. So less potent and less affinity. And then look at the tertadolol, 24.2. So if we compare the dentate gyrus, the tertadolol to the pindolol is 23.1 versus the 7.9. Similar case in the humans for the dorsal raphe. So this is how this information can be useful. If you had the data on the Wei compound versus some serotonin 1A agonist, then you would know what concentration. You'd have a good starting point to decide what concentration of this molecule to use if you were going to try to inhibit the effect of the agonist. If you wanted to use the Wei compound to study endogenous effects in the brain, you could use the KD50, the KD, as a starting concentration to test its efficacy for blocking endogenous serotonin-mediated effects that are carried out through the 5-HT1A receptor. So these are how these numbers are useful in the practical sense of evaluating whether or not someone in a research report used an appropriate dose or concentration, or if you're trying to decide for your own experiment. Now, these type of data can also be produced using the the in situ autoradiography, looking at where the radiolabeled ligand has bound. And this is with the Wei compound to generate that data we saw in the prior table. Here is a total binding, and then here is a non-specific binding, and then this is competing it off with one of the drugs, might have been pindolol, 1 nanomolar, 10 nanomolar, 100 nanomolar, 1 micromolar. You see that the 1 micromolar of cold actually prevents any binding of the radiolabeled ligand completely. So it's a competitive type of a binding study between the cold, the unlabeled molecule at different concentrations versus keeping the concentration of the labeled molecule the same. So some of you might recognize that this is the midbrain with the cerebral aqueduct shown here and the very end of the cerebral cortex in that area, and this is characteristic of the dorsal raphe nucleus. So we see the non-specific binding is low, and the 1 nanomolar is less effective at preventing the binding than is the 10 versus the 100, and the 1 micromolar prevents all binding, brings it down to the non-specific level. And so that was the rat, and then this is showing the similar data from the human. So the cerebral aqueduct is shown here. This looks like maybe the inferior colliculus, telling us that it's the midbrain. And this is the dorsal raphe nucleus, non-specific. 1 nanomolar, 10 nanomolar, 100 nanomolar. 1 micromolar didn't quite get rid of all the binding of the tritiated Wei 100635. Did I say those numbers right? This is the type of approach for the in situ radioligand binding assay using an autoradiography. This looks like it's a gel emulsion coating, since we can see the outline of the brain tissue, but still it may have been just X-ray film, and there's that much binding of the ligand to let us see some of the other general anatomical areas. Optical density would be used to measure or get some index of the intensity of the silver over the area of interest. And obviously you can see that the optical density would decrease as you progressed through these concentrations, and that data, along with knowing how much specific activity of radioactivity was in your molecule, let you come up with the concentrations that you showed on that we saw on the table in the previous slide. So this is an example of how the KD and the KI can be useful. You have to know the KD first for this whey compound, so that you know that you're getting a total binding of all the receptor sites. You'd use that concentration that just would be giving you the B max to produce this signal. So you're labeling all of the receptors, and then you can measure effectively the KI for another molecule to compete for those binding sites. Well, let's use the enzyme system again to begin to think about the Ki. So we start by thinking of the significance of the Km and the Vmax. So again, we have the K2. If it is very small, so you're more likely to proceed in this case from enzyme to substrate to the enzyme substrate form to produce the product. Then it would be equal to the dissociation constant for the equilibrium between these two, the enzyme plus the substrate to the enzyme with the substrate bound. So that KD is a measure of how tightly the enzyme binds the substrate. So we see it's the same thing. How tightly, it's an index of how tightly one thing is bound by another. It's similar to a Ka for dissociation of an acid. So what is the affinity of an acid for wanting to hold its hydrogen ion, the proton, to it? So the Km is an appropriate measure of the affinity of the substrate for the enzyme. So we see this generalization and the utility of these kinetic analyses. Obviously things are going to be a little bit different for each of them, but it tells us kind of the same story all the time when we look at them. Now the Vmax is comparable to the Bmax, so the concentration of substrate at which you get maximum binding to the biologically active site on the enzyme, and the Km are the two parameters that define the kinetic behavior of an enzyme as a function of the substrate concentration. So the Vmax is is a rate measurement of the enzyme at full speed. So the highest concentration of the substrate for the production of product is one way to measure it. The Vmax is the rate of the reaction. It will have units of, again, concentration. So in this case, the amount of product produced per milligram of enzyme. We saw femtomoles per milligram of protein as the Bmax for the receptors. Here we would have femtomoles maybe of the product per milligram of the enzyme. Not concentration, I got off track there. Km obviously is going to be in concentration, in this case, concentration of the substrate. So if the substrate concentration is much higher than the Km, then the speed, the rate of the reaction without an inhibitor will be close to the Vmax. So again, like I said, when we're going to look at the K sub I for receptors, we would want to know the concentration that produced Bmax, so we could use that to make sure we had everything bound, and that's all that our unlabeled competitor can bind to, is what the radiolabeled signal generating ligand could have bound to. So if your radiolabeled ligand can't possibly cover or bind to all the available binding sites, when you add the cold, it can bind to the available binding sites, as well as compete for the unavailable ones, and you would get faulty data. So you have to work at a concentration that is close to that maximum binding for Bmax or maximum velocity for enzyme analysis. So the Km is a concentration, and we'll have the units of milligrams per ml or millimolar, whatever the units might be for the particular substance under investigation. But it would be concentration. So why is it a mistake to call a Km the dissociation constant of the substrate? Only in one model of how enzymes work, and that of the steady state presentation, does Km equal the Kd. So it's only under certain conditions where it would almost be the same, or under ideal conditions where it would be the same. So to prove that this model was the only one that described your data, you'd have to show that the condition was met, that K minus 1 and K1 times the substrate concentration are much faster than the K2. So by some other means. The steady state studies can tell you that, and a general rule is that the Km is not the Kd. It is only Kd if you can prove it by some other method. So that's not so essential for what we're thinking about for the pharmacokinetics of receptors, but it reminds us that these are estimates of actual values dependent upon the type of method that is used. The in situ approach is not as accurate and sensitive as the crude homogenate method. The isolation of the receptor proteins, or just the membranes that would have those proteins, is going to be better, and so on and so forth. A bioassay might give you slightly different values for Kd and Ki for certain ligands than would any of the other methods that were mentioned. So within the context of the experimental design, these numbers can be estimated. If you already have a number, hopefully from the most sensitive method, such as isolated membranes that would have the receptors, then you can use the Kd or the Ki for an agonist or antagonist, respectively, and use that concentration as a starting point to begin your experiments for a dose response above or below that 50% point, and it should give you some degree of predictability. As well, if you're going to be critical of literature, this is the important question to ask. What is the Kd or the Ki for that particular drug, and how does that relate to the concentrations that you used? So if you are injecting a drug into the brain, it's a dense tissue, you have to expect some diffusion and dilution into the interstitial fluid compartment, so you might use a concentration a little bit higher than the Kd, but if the Kd is nanomolar and they're using millimolar concentrations, it's garbage. So the method for determining the Ki, again, this is the enzyme. The dissociation constant, Ki, can be determined from the rate of substrate hydrolysis without the inhibitor. So this is the V sub O. We saw that, get the total binding. And there's a formula for this, and we're not going to be too awfully concerned about that. Even though the formula will show up throughout, we're not focusing on that. I don't expect you to remember any of these formula, as I had stated in prior lectures on this radioligand binding assay lecture series. So in a competitive system, so this is what's important, competitive system. If you go back to the slides at the end of the last portion, the first half of this slide set, last portion of the previous lecture, you'll note that certain criteria are set down. These systems don't work well for allosteric types of ligands that bind somewhere else on the receptor and change it so that its response to the ligand at the ligand binding site is altered. And there's a few other examples as well. So these are really only for competitive types of systems where the molecule you're testing is competing directly for that binding site that the endogenous ligand uses. So this also is a competitive system. You have to use a competitive inhibitor. The rate of the substrate hydrolysis after addition of the inhibitor is shown here. So we get this VI and VO, and as we saw, we use different concentrations of the cold molecule, the inhibitor, so you get a ratio of the total binding to the binding with the inhibitor present. Whatever would be inhibiting the binding of the way 100635, as we saw, like the pindalol or the tataltaleol. I know that's not how it's pronounced, but I can't remember it. It's a tatalol, right? And then there is a ratio formula shown here, and you notice that you end up with a Ki applied. And this is basically what is observed, and then somewhere within here is an actual Ki. But we see that the critical evaluation of the Ki is the concentration of the inhibitor divided by the ratio of total divided by the level of signal at the inhibitor -1. So again, the formula isn't so critical as much as it is looking at the factors that are involved. The K sub I is the concentration at which you get 50% inhibition of the binding. So we see it coming forth even from this formula of estimating a Ki for an enzyme substrate reaction. And I'm just going to jump past that and go to this figure. These are less than ideal slides, as I had stated, for demonstrating this, but that's fine. So in this enzyme assay, the VO over VI -1 graphed against the inhibitor concentration produces a positively related line, so a positive slope, and that slope equals 1 over the Ki. So the larger the Ki, the smaller the slope. So a steep slope, the greater the slope, the smaller the Ki, means a lower concentration is more effective. So the value of looking at this graph is that we can take it and interpret how to predict, use it to interpret information on how to predict the impact of Ki on the slope of the curve. So the greater the slope, then the smaller the denominator must be here. The smaller the Ki, so the 50%, if we increase the slope on this, 50% inhibition would fall at a lower concentration of the inhibitor. So just to ignore those other slides, I'll have to clean all that up someday and re-record this for future use. Forgive me for such confusing information. But this is an important point, and we do want to spend some time on this, distinguishing between binding sites and receptors. So my definition of a receptor is the functional complex. We've seen G-coupled proteins and a variety of other types of receptors, and noted that the binding sites might be on just one subunit or just one location of a receptor protein. And so if you homogenize tissue or you do the in situ labeling with the dead brain tissue samples as we saw, then you don't know if there's any functional relevance to that. It's just the kinetics of the binding of biological molecules. We saw that that was uniform almost regardless of what type of binding you were looking at, at least of similar stoichiometry. Then the kinetics are basically the same, so that's valuable information, but without some type of a bio or functional assay, that analytical assay data really is of minimal utility when we try to interpret the biological relevance. It certainly would be important to you to know that the dose that you'd receive if you were taking some compound, such as that whey compound, to treat a disorder. We certainly appreciate that, but we would hope that subsequent to these types of analytical tests, some type of preclinical and clinical test was run on whole biological systems, whole animals, to work that out. So this is really an important distinction between the binding site and the receptor that's the complete complex that produces the functional response. So the binding sites are not always equivalent to receptor sites. Only binding sites that are linked with some of the biological action are considered the actual receptor, as we had stated. So other tissue sites may bind. This is a point I didn't make. We saw the non-specific binding slide. So some of what you're measuring might be non-specific binding, maybe a lipid and a protein binding. Some substances even bind ligands with the characteristics usually associated with other receptor binding sites, like opioid binding to glass wool fibers. So there are potential sources of artifact from the methodological procedures. But the true receptor binding has several properties not associated with non-receptor binding sites, and those are what we see here. So a series of studies would have to be completed to demonstrate that the binding data is reflecting the true receptor, at least kinetically even, for the specificity. So these properties form the criteria that must all be met to consider a binding site as a true receptor. So it has to show saturability. We saw that. Binding should plateau with the increasing ligand concentration, indicating that all the receptor sites can be occupied. Regional distribution, so the receptor sites should be found only in tissue known to contain biologically active receptors for the ligand. We saw that in the example of the different subregions of the hippocampus in the rat and human, and the dorsal raphe, where the neuron cell bodies were located for the serotonin neuron cell bodies, that is, known to express the 5-HT1A receptors. The pharmacological specificity, so other compounds known to bind with a given receptor population should displace the radiolabeled ligand. So not only using the cold, unlabeled, identical ligand against the labeled one, but also, as we saw, using pindolol and some of the others to evaluate it, showing that it behaves in the predictable fashion. So these other compounds were known to bind to the 5-HT1A receptor, and the binding potencies should correlate with the potencies in producing a biological effect. So there should be this linkage between the KD and the KI values in concentration, and concentrations that produce roughly half maximal responses, or inhibits half maximal response for the KI in a biological system, some type of biological functional assay system. Could be cell culture, could be organ culture, could be whole animal, whatever it might be. So any stereoselective binding should correspond to a stereoselective biological effect. We saw both the plus minus and the minus forms of the drugs that we observed. So there was a test for the stereoselectivity built into that one study we evaluated. The kinetics, so the dissociation constants from the binding data should correspond with dissociation constants from pharmacological data. So again, there should be the correlation between just the receptors and the membranes, or even if possible, just the receptors in a homogeneous solution, giving you certain numbers that should be quite close, reasonably close to what you would get in a full biological system, the pharmacological data. And denaturation, so most receptors are presumed to be protein, thus exposure to denaturing conditions, boiling, high pH, should destroy the binding. So again, this description takes into account both the analytical type of methods of assessing the binding sites and the functional. Therefore, altogether, collectively, you have a good set of data to assess receptors in a certain system. Now, sometimes the only interest is binding sites, and that's not a problem. So let's take a look at a couple of examples of passages, basically from abstracts, to see how such data might be reported. So we found that the bullfrog testes had specific gonadotropin binding sites of only a single type, which have the same affinity for both FSH and LH. So here's a species that has just one receptor for both gonadotropins with the same affinity. So the affinity, the equilibrium constant of dissociation, or KD, see how they're kind of equating those two, but that's fine. We're more comfortable with it now. We realize it's the reciprocal. So the KD is a reliable index of the KA. And the capacity, the Bmax, the number of binding sites, for FSH were 0.49 nanomolar. That's got to be KD, its concentration. And 0.27 femtomoles per milligram of fresh tissue. That's got to be the Bmax because of the units, respectively. And those for LH were 0.53 nanomolar. Not so different, actually probably not statistically significantly different from that of FSH, therefore comparable or the same, essentially, affinities, and 0.23 femtomole per milligram fresh tissue Bmax. So those are also comparable or equivalent. So when each of them were determined independently. So specific binding of the labeled FSH, so the FSH is the labeled ligand in this case, it's the radioligand, was completely displaced by both cold FSH, unlabeled, and LH, and their competition curves were identical, as we would predict from these KD. The affinity should indicate a very similar Ki between the two when they're inhibiting the binding of the radioligand. However, when labeled LH was used, the slope of the curve for competition by FSH was much gentler than that of the curve for the competition by LH. That's somewhat non-committal, but anyway, so if the slope of the curve was gentler, what is this telling us? A large amount of FSH, about 5 micrograms per ml, was required to replace labeled LH and to reduce the binding of LH to the nonspecific binding level. So it's looking like the LH is going to be favored when it is present. So to explain this result, we assume the model of nonlinear cooperativity by heterologous hormones, in which the affinity for LH of the binding site is increased in proportion to the number of sites occupied by FSH raised to the C plus the H power, where C is a constant, when the observed equilibrium parameters were employed and appropriate values for C and for KF, the KD for completely occupied binding sites. Remember, I keep saying the KD 50, well, this KF is the KD 100, were chosen as 1.45 and this number respectively. The theoretical curve for the competition by FSH against labeled LH coincided almost exactly with the observed curve. So the positive cooperativity between cooperative action of FSH on the binding of LH was also shown by association experiments, but not by dissociation experiments. So the positive cooperative action of a heterologous hormone may be a device developed in anurins to overcome the problem that one of the two gonadotropins competitively inhibits the action of the other when both gonadotropins are secreted simultaneously. So this is an example of an evolutionarily significant development where there was only one receptor but two ligands to accomplish two distinctive biological tasks, if you will. So the specific binding site of follicle-stimulating hormone in the homogenates of the testes of birds was characterized with respect to its affinity, capacity, and specificity. The usefulness of this system for radioreceptor assay to lower vertebrate FSH was also studied. So the apparent equilibrium constant of dissociation was obtained for the specific binding of rat FSH to homogenates of testes of the Japanese quail. It was 4.1 times 10 to the 9 molar. You should be, in your mind, converting that to 4.1 nanomolar almost automatically. The binding capacity was 6 femtomole per milligram of tissue, the Bmax. So we have a KD and a Bmax. The former and latter parameters obtained with the foul homogenate were 1.5 times 10 to the 9 molar and 11 femtomole per milligram of tissue, respectively. So these values are in good agreement with those previously reported in testy homogenates of white-crowned sparrows, rats, and cattle. The binding was competitively inhibited at various rates by mammalian gonadotropin preparations. The rates of competition were fully explained by the concentration of FSH contained in the preparations. The binding was also inhibited by adenohypophyseal extracts of Japanese quail and a chromatographic fraction of bullfrog adenohypophysis, but not by hypophyseal extract of salmon, so showing some bioassay systems being developed, in essence, bioassay but non-functional, they're analytical, to test extracts from other species where it may not have been known at the time exactly what's contained within them to have a gonadotropic like effect, and if it can act at receptors in other organisms. So the FSH activity of acetone dried adenohypophysis of the Japanese quail, estimated from the competition curve, was 0.14. Wow, I lost something here. And that of the bullfrog adenohypophyseal fraction was 1.14 times the NIAMD rat, or the FSH RP1, whatever those were. Guess you'd have to read the whole paper. And that of the bullfrog adenohypophyseal fraction was 3 times the FSH RP1. So the precision index of the assay was 0.09 plus or minus 0.04 standard deviation. So we can see that these approaches are useful beyond simply trying to find a drug that is useful for humans. These kinetic assays are useful for investigating the endocrine function in a variety of species when the endogenous molecules are not known. So this completes our discussion on this topic. There is two additional papers covering similar types of methods with one additional one, the radioreceptor assay, as well as the radioimmunoassay that will have to be provided in a separate lecture. Thank you for your time and attention.